Today's lecture, we're going to go over exponential functions. First, we're going to graph few of exponential functions to show you how exponentials look like and what will be the restrictions of it. Okay, so let's look at A, f of x equals to 2x. The way that we're going to graph, because we don't know the shape of exponential at this point, we're going to graph by plotting the points. So we're going to have x and y. And since we don't know the shape, let's try one negative number, 0 and positive number maybe, right? Let's start with 3, and if you feel like that if you need to plug in more points, that's what we need to do. So when we plug in negative 1 for x, here you're going to get 2 to the negative first exponent. So 2 to the negative first exponent, that's equals to 1 over 2 to the first exponent, which is just 1 over 2, right? So it will be 1 over 2. And when you replace x with 0, any number to the 0 exponent is equals to 1. So you're going to get 1. When x equals to 1, you get 2 to the first exponent, which will be 2. So let's see if we can graph that. When x equals to 0, it passes 1 right there. When negative 1 will be half. And positive 1, it will be 2. And if you want to, you can try more numbers, like maybe, what about negative 2, right? When you replace x equals to negative 2, that's going to be 2 to the negative square, which is 1 over 2 squared, that's 1 over 4. So we'll give you 1 over 4. And you can tell that if this number is getting smaller, negative number is getting smaller, you're going to get 2 to the negative 10th exponents, which is going to be 1 over 2 to the 10th exponents. So your value will never become negative, but it become really, really small. It means that it will never go under x-axis, but it will stay on top of x-axis, going close to the x-axis, but it will never cross the x-axis. So your graph will be look like that. Because no matter how small your x is going to be, your values become smaller, close to 0, but it will never be negative number. So we know that we're going to have a horizontal asymptote here. Horizontal asymptote, that's that x-axis, right? And if you think about it, if this number right here, 2, become different numbers. Let's say, what about 3? Instead of 2, if it's 3, it always passes 1, because if you have 3 to the 0 exponent, it will be still 1. Even this number become 100. 100 to the 0 exponent, it will be still 1. So all of exponentials will pass 0 and 1, this point right here. And what's the difference then? If this number is bigger, then it get more stiffer, right? Because when it's 1, that number 1 or 2, this number will go way stiffer. If it's 100 instead of 2, this is going to be, when x is 1, this value will be 100, which is way up there, right? So this angle gets stiffer, but always past this point, and you will have horizontal asymptote, because no matter how small your value is going to be, never be negative, so it will not go under. So basically, by graphing one of the exponential function, you can get the shape of the graph. So this is the shape of the graph, and always pass 0, when x is 0, y will be 1, and you have horizontal asymptotes. Okay, if this number get bigger, only thing different is going to be stiffer it gets. Okay, then if we wanted to look at the next one, very similar one, we start with 2 to the x exponents. Here we have 2 to the x minus 1 exponents plus 2. What I wanted to show you from this A to B is even exponential functions you can graph using transformations. Remember the transformation for quadratic equations, square root equations, absolute value equations, all that. We were able to use the transformations, right? Any number that is attached to x, this is going to give you transformations of right or left. Any value that is added or subtract to the whole functions, that's going to give you transformation of going up and down. So this function g of x will have same function as the f of x functions. Only thing different between 2 to the x exponents 2 to the x minus first exponent plus 2 is going to be minus 2 to the x and plus 2 to the whole functions. So only thing it's going to change is going to be going up 2 and moving right 1. Going up 2, moving right 1. So what do we know about this one? We know that it's passing 0 and 1. So if we use this point 0, 1 will be going up 2 and moving right 1. So let me draw that without, hold on, let me erase that with the black. So before it was 0 and 1, now it's going to be going up 2 and move right 1. So it will be this point. So it was 0 and 1, now 1 and 3, right? That will be the point. Your horizontal asymptote was y equals to 0, right? So this y equals to 0, you need to go up 2 and move right 1. Horizontal line, if you're moving right or left, it's going to be still same horizontal line. So right or left moving, it's not going to change, but going up 2 is going to change. So let me mark that horizontal line going up 2 from y equals to 0. So your horizontal asymptote is going to be positive 2 this time. Where this one was 0, at 0, right? So this is 1, this is 3. So with the same shape, going close to horizontal asymptote, but never cross the horizontal asymptote. So this is how your graph will look like for g of x. I didn't have to plug in any points because I'd be able to use the transformations, right? So this one right here, I went up 2. This number right here, I move right 2, right? Let's look at one more. We have C. What about if our base is fractions? Let me plug in the points. So when x is negative 1, 0, 1, I always like to try one with negative, one with positive, and 0 is the easy number to use. So when x is negative 1, 1/2 to the negative 1. And we know in order to get rid of negative exponent, we flip the base. So this becomes 2/1 to the first exponent, which is just going to be 2, right? So this is going to be 2. And when we let the exponent equals to 0, any numbers to 0 exponent will be 1. When x equals to 1, it will be 1/2. So when we graph this is going to be 0 and 1. Remember I said always pass 0 and 1 unless you have plus minus here. So if you have a plus minus here outside of the functions to the whole function, that's going to be changed because it goes up and down, right? But long as you don't have any of those additions to the functions, addition subtractions to the functions, addition subtractions to the variable, it will be always 0 and 1. When x is 0, y will be 1, will be the points it will be passing. And then when x is negative 1, negative 1, y will be 2. And when x is 1, it will be half, right? And again, we're going to have horizontal asymptote. And when you draw this, it will be look like this. Going close to horizontal asymptote, but never pass because it will never be negative numbers. So as you can see, if it's a half as a base, it will be flipped graph, right? Example 2, we're going to look at word problems. Some people might say, why do we have to go over exponentials? When are we ever going to use the exponentials in our life, right? So example 2, I have a word problem where we will use the exponentials. Okay, so previous math class, you probably look at the interest formula before, and one of the interest formula you're looking at it was the simple interest formulas. You have formula for simple interest formulas, which is interest is equals to P RT, principal time, rate times times. So this is one of the formula we use when it comes to interest problems, right? We have another interest formulas where amount is equals to principal times 1 plus rate over n to the nt exponent. And this is going to be compounding interest formulas. What's the difference between? Well, the simple interest is that we're going to look at it every year, there will be no changes in that years. This compound interest means that you can compound your amounts different terms. So if you wanted to compound your principal every month, that's going to be compounding monthly, right? So every month your principal will change. If you wanted to compound quarterly, you have 4. So if you're going to use the compound quarterly, your n value is going to be 4, because quarterly means you have 4 times a year, so n is going to be 4. So if you do the compound quarterly, you're going to change your principal every quarter, right? You have compounding monthly, compound daily, all these different options. In that case, you're going to use these formulas. So when we're reading this problem 2, example 2, it says suppose that 5,000 is invested and pays 6.5% per year under the following compounding options. So whenever you see the compounding options, then you're going to use this formula instead of the simple interest, right? We're not using simple interest because your principal will stay same. Compounding is going to be principal changing. The part A is find the total amount in the account after 1 year with compound annually. So this one means that compound annually means you're going to have recalculate your principal every year. So then let's look at A. We know which formula to use, right? This is the formula you're going to use. So then we need to find the principal. What's P is going to be? P is principal, how much you're going to invest. And then your rate is 6.5%. And when you change that to the decimal, it will be 0.065. And under the following compound options, A, your compounding option is compound annually. So compound annually, you're going to use n equal 1 time. And then what's the year? T will be 1. With that information given, we should be able to replace it in the formula. So your total amount A will be principal times 1 plus 0.065 over 1 to the 1 times 1. And when you simplify that, you get 5,000 times 1 plus 0.065. 1 times 1 is 1. And if you have a 1 exponent, it's same as not writing down, right? So then this is same as 5,000 times 1.065, which you get 5,325. And that's the total amount, your principal plus the interest. So because your principal was 5,000, your interest is 325 if you compound annually. So then let's look at the second one. What about if it's with compounding quarterly? So same information, but this time you wanted to compound quarterly, right? So we're going to say P is equals to 5,000. Same principle. Your rate is also 0.065. Your N is compound quarterly. Compound quarter means 4 times a year, right? And your T is going to be 1. So all the information is same except compounding period. It was 1, now it's 4 times a year, right? So let's see what we get. Total amount is equals to 5,000, 1 plus same interest over N. Your N is 4. And NT, so it will be 4 times 1. So then when you replace that, you get 5,001 plus, if you replace 0.065 divided by 4, you get 0.01625. And 4 times 1 is 4. And this is going to be 5,000 times 1.01625 to the 4th exponent. And then when you plug in all that number into the calculator, you will get 5,333.01. So when you're comparing these two numbers, this is total amount you get when you compound yearly. This is the amount you get when you compound quarterly. So 4 times when you compound per year, you get this is 25.33, so you get a few dollars more, right? So obviously this is more amount. You have 325 from this one, just the interest. This one right here, just interest itself, is $333.01, right? So this one is obviously better options if you wanted to have to pick one out of those two. So as you can see, some of the word problem, and later on, once we are done with other sections, we're going to go over different types of word problem where we're going to use exponentials, right? Exponential usually come with logarithmic function, and that will be our next sections. But we will use exponentials and logarithm for some of our word problems. Okay.